Hello. So we're going to start Laplace transforms. And so I guess we'll start with the question of what is a Laplace transform? So it's this really neat little device. We can think of it as a machine. And I'm just going to give it, so for Laplace transforms, we use the script L for Laplace transform. And as a device, as a machine, it has an input and it has an output. Right? So the input is going to be some function. I'll call it f of t. That goes into the function. And what comes out is another function. I'll call it capital F. The interesting thing is, though, it's not a function of t anymore. It's a function of another variable we'll call s. Okay, so it basically takes a function in t space and transforms it to a function in s space. So these two functions don't even live on the same space, right? So let's say this is my f of t here. And for these functions, the domain will invariably t is greater than or equal to 0. So we'll see that that's not such a bad restriction. After all, if we think of t as time, then we start our clocks at time t equals 0. Right? So, yep, so then you transform to another function, and this again may look very different, right? And so, well, in this case, s could be greater than 0, but it could shift either left or right. But for now, let's just say that s is also greater than or equal to 0, or typically just greater than 0, actually, in most cases. Yep, so that's what the Laplace transform does. It transforms one function, right, with this domain, transforms it to another function, but it also transforms the space that it lives in. So the input functions live in t space for time, and then the output functions live in s space for s. Okay? So here's the definition. Here's what it actually does to this function, right? So this is our definition. So again, we're given function f of t that's defined for t greater than or equal to 0, right? And then we get the Laplace transform of this function f of t, right? Which we can also call capital F as a function of s. And here's how to calculate it, right? At least using the definition. It's defined to be the following definite integral. We're going from, t goes from 0 to infinity, right? So it's actually an improper integral. And we're going to integrate e to the negative s times t times whatever f of t was, right? And we're integrating through t. So you can see now why this is a function of s, because we're integrating out the t, and what remains will be in terms of s. Okay. So when doing this integral, we can think of s as a constant. I mean, that's how you evaluate this. That's how you evaluate this integral, treating s as a constant. But once you calculate that, then we're going to think of this as just varying in terms of s, okay? So when you do the integral, s is treated as a constant, right? T is the variable, and then you get some quantity that will depend on s in most cases, right? All right, so let's just do a bunch of examples to see how this works. So what functions should we take the Laplace transform of? Well, let's do the most boring one I can think of. How about just 0? Obviously, if f is 0 here, then 0 times anything is 0, and when you integrate 0, you just get 0 So the Laplace transform of 0 is just 0. Almost not worth mentioning, right? But, you know, that's our first example. For our second example, we'll do something slightly more interesting. How about 1? So what's the Laplace transform of 1? Well, according to the definition, it's going to be the definite integral from 0 to infinity of e to the negative s times t, right, times 1 dt. Right. So this one's not hard to figure out here, right? So the integral of e to the negative st is 1 over negative s, right? You do a substitution there. E to the negative st, and then we just evaluate between 0 and infinity. And now I'm being a little sloppy here, right? You can't plug in infinity here. What we're going to do, though, is we're going to take the limit, right, as let's say b goes to infinity of negative 1 over s, e to the negative st, and then integral, and then we evaluate this between 0 and b. So when we do that, right, we just get negative e to the negative s times b over s, and then minus a negative, so plus 1 over s e to the negative s times 0, which is, well, 0, e to the 0, right? So, yep, when you take this limit, right, as b gets bigger and bigger, e to the negative b, or negative s times b, gets smaller and smaller, right? It goes to 0, right? So this is 0 plus 1 over s times 1, which is just 1 over s. Okay, so, yep, so there's our first sort of non-trivial Laplace transform. The Laplace transform of the number 1 is 1 over s. And of course, right, as I said earlier, s is going to be greater than 0 here. Okay, so, yep, keep that in mind. Yeah, so I'm going to use this notation over and over again, right? So we're pretty much going to treat e to the negative infinity as just the number 0. Again, this is you know, really sloppy here, but because it's really the limit as x goes to negative infinity of e to the x that becomes 0. So yeah, so it's more, maybe somewhat more appropriate to say that this approaches 0, well, right, as x goes to negative infinity. So, yeah. So e to the x approaches 0 as x approaches negative infinity. Or maybe we should do it the other way, right? E to the negative x approaches 0 as x approaches positive infinity. Right? But, yeah, from now on, just take for granted that e to the negative infinity is 0. That's sloppy notation, but we're going to use it. Okay, let's keep going. Let's do a bunch more. So how about f of t is just equal to t itself, right? Yep, so the integral then, I'll do it down here. The Laplace transform of t is the following integral, right? You're going from 0 to infinity of e to the negative st times t dt. So, yeah, this one's a little trickier because this one, you might remember, this has to be done by parts. So we'll integrate by parts. I suppose u will just be t. So du is dt. And my dv then will be e to the negative st dt, which means v is negative 1 over s e to the negative st. Right? So, well, yes, just to remind you, the integral of u dv is uv minus the integral of v du. I'm sure you all know that. So let's apply that, right? So u times v is going to be negative t over s, right? E to the negative st. And then we evaluate between 0 and infinity. Again, sloppy, but get used to it, right? It's a lot easier than having to go through all these limits again. You know, once you get used to it, it almost becomes second nature, right? And then minus the integral of v du. So we have minus a negative, right? So that's going to be plus 1 over s. We can take outside because it's a constant. And then just the integral from 0 to infinity of e to the negative st dt, right? So let's evaluate this first term here. So what happens when t is infinity? Well, you get infinity times 0, which, you know, so if you use L'Hopital's rule, you'll see that you get 0 here. And then minus, when you plug in 0, well, you also get 0. So this is really just, you know, 0 minus 0, or technically negative 0 plus 0. So yeah, this whole thing just goes away, right? Just becomes 0. All right, so what about the second term here? So we have plus 1 over s. Well, if you're clever, you realize we did this already, right? That was the Laplace transform of 1, which we said is 1 over s. So we get 1 over s times 1 over s, which is 1 over s squared. Okay, so, and again, s has to be positive, right? So that's the Laplace transform of t. Maybe I can squeeze it in here. The Laplace transform of t is 1 over s squared, and that's for s positive, right? Okay. Again, I know these are all in the book, but I'm trying to go through it step by step here. Yeah. So, right. So you might consider. So you know what? I'm going to switch variables here. But before we do the next example, let me go back up here. So you're not always going to see f of t. You might see x of t. So if that's the input function, the output function will be capital S as a function of s, right? And if let's say the input function is y of t, then the output will be capital Y of s. So yeah, just use the capital letter for the Laplace transform. So in other words, right, this is, yes, right, so this is f of s equals 1 over s squared here. Right, same thing. All right, so now we could probably consider, I'm going to do x of t. We can just do t squared here, right? So what's the Laplace transform of t squared? Well, you might think, well, then it's just 1 over s cubed. So close, but not quite. Right. So you do this integral, and you can see you're going to have to use Laplace, integration by parts, but you're going to have to do it twice. Okay, and I'll let you work through it if you want. So it's just slightly more tedious. What you're going to end up with is 2 over s cubed, right? So where did the 2 come from? Well, I could say because you're doing it twice, but that's not quite right. So again, s has to be positive. So let me just give you the general formula here. If you do t to the power n, right, for any exponent, what you're going to get is n factorial divided by s to the power n plus 1. Okay. Yep. So here, if n is 2, 2 factorial is 2, right? When you did t to the 1 up here, right, and 1 factorial was 1. And of course, this works for n equals 0, right? 0 factorial is 1, and then this is s to the 1, right? Which is just 1 over s again. So yes, so obviously this only works for, integers 0, 1, 2, 3, and so on. Yeah, there's a more general way to do this for non-integers involving something called the gamma function. So some of you may be aware of this gamma function. And it is just equal to n minus 1 factorial when n is an integer, but this is more versatile. You can use, n is 1/2, or even, irrational numbers like pi, for example. So we're not going to get into that. For the most part, we're not going to need this, I don't think. It may come up in the homework, but I wouldn't worry too much about it. Okay, so we have basically t to any power, and, for at least to any integer power, or non-negative integer. All right, so what about the more interesting ones? Let's do about y of t is equal to, how about just e to the at? So here a is a constant. A is just a constant, right? So for some constant a. Right. And in fact, a could be anything, positive, negative, that doesn't matter, right? Yep, so let's just do, supply the definition, right? So the Laplace transform of e to the at is going to be the definite integral from 0 to infinity of e to the negative st, right, times e to the at dt. So you can see that this simplifies greatly if we just write this as e to the a minus s times t dt. So we don't even have to do an integration by parts here. All we have to do is a substitution, right? U is the exponent, a minus s times t. So the du will be a minus s, so now we have to divide by a minus s. And then we just get the, right, e to the a minus s times t, evaluated between 0 and infinity, as usual. Well, now we have a problem, right? If s is less than a, then this is gonna diverge. But if s is bigger than a, right? In other words, a minus s is negative, then it converges to, well, the usual 1, right? So this is 1 over, oh, you're subtracting 1, right? So negative 1 over a minus s, which is actually 1 over s minus a. So here's another one. The Laplace transform of e to the at is just 1 over s minus a, as long as s is bigger than a. Right? So effectively, yeah, we're shifting our domain here to the right. Yep, so gradually we're building up our library of Laplace transforms, just using the definition here. And I'm debating about whether I should do one more. All right, we'll do one more, and then move on. So yeah, so let's just do the Laplace transform of sine of k times t. Okay, so by definition, that's the integral 0 to infinity of e to the negative st times sine of kt. Again, k is a constant. K is a constant, right? Okay. Well, yep, this is another integration by parts. So u, of course, well, I think it works both ways, but let's do u is equal to e to the negative st here. And then dv will be sine of kt. See? So du will be negative s. Oh, I think I wanted to do it the other way. Yeah, let's do it the other way, I think. Well, you know what? I guess it doesn't matter. All right, so negative s e to the negative st, right? And then v is 1 over k, negative 1 over k cosine of kt, right? Derivative of cosine is negative sine, right? Okay, so I think, yeah, this will work. I don't think it matters which one you call u and which one you call dv here. All right, so let's see what we get, right? So we get u times v, so that's going to be negative 1 over k e to the negative st times cosine of kt, evaluated between 0 and infinity, and then minus v du, so that's going to be minus a positive, minus 3 negatives, right? So that's still negative s over k times the integral from 0 to infinity of e to the negative st cosine of kt dt. Okay. So let's look and see what we have on the left here. When t is infinity, cosine of infinity is, well, it varies between negative 1 and 1. But this goes to e to the negative infinity, which is 0, right? And then when you plug in 0, cosine of 0 is 1, and e to the 0 is 1. So you really just get minus a negative 1 over k. So you get 1 over k. Okay. And now what's this integral here? Well, yeah, we got to do this all over again, right? We have another integration by parts. So this time, no, we'll do the same thing. U is going to be e to the negative st. So du will be negative s e to the negative st. Or dv will have to be cosine of kt. And then v will just be 1 over k. Sorry, k sine of kt. Okay. Yep. So we got to do this a second time, right? So minus s over k, that stays there. And now, I shouldn't use just use a bracket here, right? So u times v is going to be 1 over k times e to the negative st times sine of kt, evaluated between 0 and infinity, and then minus v du. So now it's going to be minus a negative, so this will be a plus. I think it's s over k times the integral from 0 to infinity of e to the negative st times sine of kt dt. Okay, so let's see, we get 1 over k, and then we can distribute this. This is minus s over k squared times, well, now you get e to the negative infinity, which is 0, minus sine of 0 times 1. Sine of 0 is 0, so you just get 0 minus 0 here. So that's just 0, right? Minus, and now distributing this, we have s squared over k squared times, well, this integral, right? So now it seems like we're running in circles because that was the original integral that we wanted to do here, right? So yeah, this is what we wanted to do. Let's just give it a name. Let's call it, let's just call it capital L, right? So this is all equal to L, right? Which means L is equal to 1 over k minus s squared over k squared times L. So we just have to solve that equation for L, right? And it might help to get a common denominator here. So this is going to be k over k squared minus s squared over k squared times L. If you add this to both sides, you get L times 1 plus s squared over k squared, and that's still equal to, oh, then we didn't need to do this. Oops. We'll just leave it as 1 over k. Yep. So, yeah, I don't know why I was going to get a common denominator. We needed to add this term to both sides. So, oh, yeah. Yeah, so this is just 1 over k. So I should have left this as 1 over k. All right. Anyways, right, now we have to divide. So L is going to be 1 over k divided by 1 plus s squared over k squared. So to get rid of the compound fractions, just multiply by k squared over k squared. And you end up with k over k squared plus s squared. Although I think it's more common to put the s squared first. So that's L, right? And that was the Laplace transform. So let's just make that official. The Laplace transform of sine of k times t is equal to k over s squared plus k squared, or k squared plus s squared. But this is how it appears in the book, right? Okay, so there you go. And without having to go through this all over again, let's just note the cosine of kt, its Laplace transform is going to be s over s squared plus k squared. Okay. So, yep, very similar calculation, of course. You still do the integration by parts twice, and then solve for the one side, which I'm calling L just for convenience. Okay, so I think we have quite a few Laplace transforms, and of course, on your formula sheet you have a whole bunch more. And what I should say right now is, if you want to figure some other ones out, like maybe hyperbolic cosine, or maybe combining these, you can do e to the 3t times sine of 5t. Doing this by the definition here is very tedious in most cases, right? The ones we did here this is using the definition here. These are all very reasonable to calculate using the definition, right? But at some point, it gets to be way too tedious. And so I wouldn't go much further than that for calculating Laplace transforms using the definition. And I don't know if I gave you this one for homework, but I think this one's in the book. It's the Laplace transform of, say, t times cosine t, which I just think is sort of nightmarishly difficult and tedious. So I would not recommend going through that unless you really want to. Because there are tricks. We're going to learn some tricks or techniques to be able to calculate even something like this, although that's, well, to be fair, this is one you would probably still use the definition, as bad as it is. Right, so we're not going to get too far into the techniques for, say, t times cosine t. Yeah, for other functions, like let's say you want to do sine plus cosine, or, e to the 5t plus sine of 7t minus 6 cosine of 4t, or, The nice thing about the Laplace transform is that it's linear, right? It is a linear transform. Okay, so it is a linear transform. And what we mean by that is the following. If you take the Laplace transform of some constant, let's say alpha times f of t, plus beta times g of t, some other function g, right, that you can just pull out the alpha, and then the Laplace transform of little f is capital F of s, right? and then pull out the beta. And let's say that the Laplace transform of little g is capital G, again, as a function of s, right? So that's what it means for something to be linear, right? And since I'm out of space, I guess I'll have to start over. So give me a second, and I'll start on a clean page. Yep, there we go. So I just copied down the fact that L is a linear transform. So you can think of L for linear, but it's actually for Laplace. I think it's Pierre-Simon Marquis de Laplace who came up with the Laplace transform. Although I'm sure Euler probably did a lot with it as well. Maybe came close, but Laplace got the credit as usual. Anyways, so with that we can let's do another example. Let's do the Laplace transform. I should call this an example. Let's calculate the Laplace transform of hyperbolic sine of, let's do kt. I was just going to do t if k is 1. But we can do this more generally, I think. So we're still going to use the definition, actually, no, I don't think we need to use the definition. Never mind. Here's how we're going to do it, right? You have to remember what hyperbolic sine is. It's just e to the, I think it's k times t, right? Minus e to the negative k times t all over 2. Okay? So that's how we're going to calculate the Laplace transform of hyperbolic sine, right? We're just going to calculate the Laplace transform of, 1/2 times e to the kt minus e to the negative kt. So the 1/2 is a constant, and because Laplace transform is linear, we can take that outside. Oops, sorry, the positive k comes first. Right. And also because it's linear, we can split this up as the transform of each of these separately. Again, we wouldn't be able to do that if this were not linear. Right. Again, why is it linear just comes from the definition, right? The integral from 0 to infinity, is a linear process. You have the sum rule for integrals and a constant times function rule for integrals. So that works there. Now, we did this already. Just to remind you, we did the Laplace transform of e to the at. We called it a in that case. And the Laplace transform was 1 over s minus a for s greater than a. So the only difference is we're not calling it a anymore, we're calling it k. But there you go. So this will just be 1/2 times 1 over s minus k, right? It's an s. And then minus 1/2 times 1 over s minus negative k, or s plus k. Okay. So, now that I think of it, we could have left the 1/2 in front, so let's factor it out again. And when you do that, you get 1 over s minus k minus 1 over s plus k. But I think you know what to do from here, right? Just get a common denominator. So you get s plus k minus s minus negative k, so another plus k, divided by s minus k times s plus k. And you see what happens here. You get s minus s, and then you get 2k divided by 2, which is just k. And then this just becomes s squared minus k squared. So, the 2's cancel, and in the end, we just get k divided by s squared minus k squared. Right? And all just using linearity here. We did not have to do any more integrals. So yeah, remember when I said not too long ago that when you're calculating Laplace transforms, you're not going to use the definition all that often anymore. You might have to in some cases, but using this trick of linearity and using the ones we did already, right? In other words, we had to know the Laplace transform of, say, e to the kt and e to the negative kt. But knowing those, we can just sort of build up more functions here. So this is for hyperbolic sine. So maybe I'll mention that. The Laplace transform of hyperbolic sine, or sinh of kt, is just k over s squared minus k squared. And by a very similar calculation, of course, you can get hyperbolic cosine, or cosh, of kt. And that's going to be s over s squared minus k squared. Okay. Yeah, in fact, very similar to the sine and cosine. The sine and cosine are the denominator is s squared plus k squared. So yeah, that's the only difference there. And maybe just to drive home this point, let's do one more. So I lost count of our examples, but okay, one more example. Let's calculate the Laplace transform of, let's just do e to the negative 3t plus 4t squared minus 3 cosine of 7t. Okay. Well, since the Laplace transform is linear, we can just split them up. Let's do it all at once here. Boy, that's a funny looking brace, but there you go. And then we can pull out the 4 and just take the Laplace transform of t squared, and then pull out the negative 3 and take the Laplace transform of cosine of 7t. Okay. Well, yeah, so here, this is e to the at, where a is negative 3. So this tells me this is 1 over s minus negative 3, or 1 over s plus 3. Excuse me. So plus 4 times the Laplace transform of t squared. Hopefully you remember for t squared, that's going to be 2 over s cubed. Right. And then minus 3 times, well, cosine of 7t. For cosine, I think that's going to be s over s squared plus k squared. Here k is 7, so 7 squared is 49. Right. So just putting it all together, you just get 1 over s plus 3 plus 8 over s cubed minus 3s over s squared plus 49. And feel free to leave it like this. There's no reason to get a common denominator here. I mean, yeah. So I don't think there's any reason to try to simplify this any further. Okay, so that's it. That's the Laplace transform of this mess up here. Again, just using linearity and then all the transforms that we know already. Yes. So yeah, from now on, when you encounter the Laplace transform of, let's say sine of 7t, yep, you don't have to go through the integral all over again at this point, right? So this is just going to be k, which is 7 over s squared plus k squared, or s squared plus 49. So notice that for the sine, your numerator is k, and then for the cosine, the numerator is the s here. So just keep that in mind, right? So yeah, obviously, where these come from is from the definition, but I'd say we'll use the definition maybe 1 or 2 more times. It's good to get used to the fact that this is linear, and then to be able to calculate things like this just using linearity. Okay. Okay, so the next thing we have to talk about briefly, but it's an important concept, is the existence of the Laplace transform. Again, L for Laplace transform. So it turns out that you cannot just take any function and take the Laplace transform, right? So when you take the Laplace transform of a function, f of t, let's say, first of all, we already know that t has to be greater than or equal to 0. That's the domain. Yep, otherwise, it might not work. But that's not all there is to it. So for example, if you want to try to take the Laplace transform of 1 over t, that's not going to work. This does not exist. Using the definition. And you can maybe see why. The 1 over t, right, as t goes to 0, this becomes undefined, right? So that's one issue. Another issue is that it might be growing too fast. Like, let's say we have e to the t squared. This also does not exist, right? So yes, it's, the Laplace transform applies to a lot of functions, but not all of them. So, right, so it turns out that you can take, right, the Laplace transform will exist for functions f of t that are piecewise continuous. Okay, so it's going to be piecewise continuous if it has a finite number of discontinuities, right? So like if this is t here, and remember you're starting at 0, right? So if the function looks like this, and then you have a jump here, and then you have another jump here, right? And let's say you have a jump here. As long as they're finite jumps, right, then there's no problem, right? Oh, even made it continuous here. So whatever. Let's just say it's 0 from this point on, right? Yeah. So any, sort of piecewise function, piecewise continuous function, you can break this up into its various pieces here, say at A, B, C, and so on, and D, and just do those integrals separately. And it also has to be of exponential order. So what do I mean of exponential order? Basically, it just means that the function f grows exponentially, right? But no bigger than exponential, right? So, yeah, so officially the definition just means that, right, that there exists, right, there are constants, C, M, and T, right, where M and T are bigger than 0, such that in absolute value, the function f of t is going to be less than or equal to m times e to the ct, right, for t bigger than capital T. Right. So in other words, it behaves sort of exponentially, right? And that includes a whole lot of functions, right? Any polynomial function, right? Any polynomial, no matter how big the t is, right? So this could be t to the 100th, plus 2t minus 8 or something. And yes, this grows very quickly, but you can always find a c here and an m so that, right, that the t to the 100 will be less than some exponential function. At least for some, right, once you get past a certain number, right, so t might be bigger than, 20 or something, or, some bigger than some capital T, right? In the meantime, though, when you're less than capital T, then sure, this might be, f might be bigger than this, but eventually it can only grow exponentially, right? Yeah. So going back, now you can see the problem here with e to the t squared. E to the t squared is not of exponential order, right? E to the t squared right? There's no way you can make this, right? Remember, c is a constant here. So even if I have, 1 million t, this may be bigger for, for a pretty large t, but eventually this will overpower it, right? The e to the t squared will become bigger, right? The t squared will become bigger than 1 million t eventually. So yes. So because of that, e to the t squared is not of exponential order, and that means there's no guarantee that you have a Laplace transform. In fact, you don't. Right. We already said that. It does not exist here. What's wrong with 1 over t? Because if you remember, 1 over t shrinks very quickly. So, right, but exponential functions grow very quickly. So you might think, if this is your t here, then this is going to be bigger than that. So it turns out 1 over t is certainly of exponential order. The issue is not that. The issue is piecewise continuous, right? Look at what happens when t equals 0, right? We were allowed to, t is allowed to be 0, right? But if t equals 0, then 1 over 0, is infinity, or it approaches infinity. And so this will, the integral will diverge, right? You'll get, an infinite area in here, right? So that's the issue here, that it's not continuous at 0, right? So, yeah. So the short of it is this, right? The basic idea is that if f of t is piecewise continuous and of exponential order, right, then we know that the Laplace transform has to exist. Okay. Right. So any piecewise continuous function of exponential order, so it has to be both piecewise continuous and of exponential order, then the Laplace transform will exist. Okay? But it may exist even though you can have a function that may not be piecewise continuous, or that may not be of exponential order. And it turns out that, that you can have Laplace transforms even in cases where this is violated. Again, we're not going to see those very much, but it could happen. So, for example, let's say f of t is equal to 2 e to the t squared times cosine of e to the t squared. You can show that this is also not of exponential order, but it turns out you can take the Laplace transform of this function. It does exist. Right. It's kind of a hassle to calculate it, but it is doable. Oh, wait a minute. I think I'm missing a t here. Yeah. The derivative of t squared is 2t. So 2t times e to the t squared cosine of e to the t squared. Chain rule, right? Yeah. Yeah, and then again, there might be other functions that are, say not piecewise continuous. They might have a vertical asymptote. It turns out that the function g of t is equal to t to the negative 1/2, right, which is 1 over the square root of t. That Laplace transform does exist. Right. So even though it doesn't exist for 1 over t, it does exist for 1 over the square root of t. So, yeah. But again, these are ones that are not going to come up. That's why they're in red. So if you can't read these, don't worry about it. I'm not really saying anything important here. Maybe one more property. So if you remember the Laplace transforms, 1 over s and 1 over s squared and 1 over s squared plus k squared, it turns out that the end behavior, right, if you have your Laplace transform capital F, that goes to 0 as s goes to infinity, right? So as long as little f is piecewise continuous and of exponential order, right? So remember, that guarantees the Laplace transform. Then the Laplace transform right? I should say then, the Laplace transform approaches 0 in the limit as t goes to infinity. Okay. All right, so I think that's it for the properties. Maybe we'll do one more example, just using the definition, and then we'll move on to bigger and better things. Yeah, so one more in this section. All right, I might not have enough space, so let me clear all this. And then scroll up. All right. Okay, so we have a function. It's this piecewise defined function, 0 for t less than a or greater than b. And it's going to be c. C is a constant, right? So c is a constant here for c, some constant. But only when t is between a and b. Right, so this is number 10 in the book in 7.1. And the book doesn't actually write it this way. The book just draws the graph. And so here's the graph of this function. So this will be, say, f of t here. Oh, yeah. So let's say this is a here, and this is b here. So the graph of this function is just going to be 0, right, up until you get to a. And then at a, it jumps to c, which is, let's say, up here. So this is where y is c. And then it's just a constant, right? And then it jumps back down to 0 from that point on, right? So yeah, technically there's a hole here. Right. So that's the function. So it's not continuous, but it is piecewise continuous, right? It has these finite jumps. Okay. So we want to find the Laplace transform, capital F, of this function, right? And this is one where, yeah, we're just going to use the definition again. I don't see why not. So the Laplace transform of f of t is, well, here's the definition again. Integral from 0 to infinity of f of t times e to the negative st. Although I think I wrote it backwards before, but it doesn't matter. So you can see that from 0 to a, it's just 0, and from b to infinity, it's 0. So the only finite integral we get here is from a to b. And f will just be c there, so c times e to the negative st. Right? So, yep, because c is a constant, we can bring that outside. And we've seen this integral many, many times. E to the negative st is just negative 1 over s, so negative c over s, times e to the negative st. And then you just plug in the a and the b, right? So this is negative c over s times e to the negative sb minus e to the negative sa. And I guess that's it. The other thing you might want to do here is make this a positive, so we'll switch the order then. So let's make this c over s times e to the negative s times a minus e to the negative s times b. And this is going to be for s greater than 0, I think. Okay. So yeah, this is one that's not hard to do by the definition. Yeah, I think we'll leave it at that. There's a few more in the homework, piecewise functions like this that you can figure out. But again, don't do a ton of them by the definition. In fact, in a lot of cases, it's going to say use theorem 7.1.1. And let me just check in the book. Yeah, not definition 7.1.1, theorem 7.1.1. And those are just a list of the Laplace transforms, the ones we talked about already. So, for example, the Laplace transform of 1 is 1 over s. The Laplace transform of t to the n, right, is, boy, I forgot, n factorial over s to the n plus 1, right? And so on, right? Remember the one for sine. So that's going to be k over s squared plus k squared, and so on, right? We did them already. So the theorem just basically proves them using the definition. So when they say use this theorem, what they mean is use this theorem and linearity, right? And linearity. Use the fact that they're linear. So if you have to do, say, the Laplace transform of 1 plus t cubed, then you do the Laplace transform of 1 plus the Laplace transform of t cubed, and so on. Okay? So I think that's it for 7.1. 7.1 is just getting used to the idea of the Laplace transform, getting used to this definition, and getting used to that it's linear, and once you establish all these, you can calculate them by linearity. And again, all these formulas are on your formula sheet, so in no way should you spend any time memorizing these. You can always look them up, or just refer to your formula sheet, right? So these are all on your formula sheet. In fact, it's on the same formula sheet with all the definite integrals, with all the indefinite integrals that I gave you at the very beginning of class. So yeah, so feel free to refer to that same formula sheet, not just to do integrals, right? Hopefully you don't need a formula sheet for this integral, but there's much more complicated ones that are on there, but also the Laplace transform. So yeah, don't bother memorizing these. Obviously, these might be helpful to know because they come up over and over and over again. But, for something like the Laplace transform of, t e to the negative, e to the negative at times hyperbolic cosine of kt. Yeah, this is one you can probably look up. Or if it's not on there, then I would just give it to you. But this is one you definitely don't want to try to calculate using the definition, unless you want to pull your hair out, because this could take hours and hours, and it's not worth it. So yes, mostly make sure you at least understand what a Laplace transform is. That it takes a function and then produces some other function, but not as a function of t, as a function of s. So just be aware of that. And, the business about exponential order, that doesn't come up very much, because all these functions that we are going to take Laplace transform for will be of exponential order. In other words, the Laplace transforms will exist. But, yeah. So that's 7.1. And I think this is everything you need for the homework. I don't think the homework is that bad. Most of it is routine. Some of it might be tedious because of, calculating these integrals might not be as easy as the ones that I've been doing. You might have to do integration by parts, sometimes several times. But that's about it for 7.1. I hope that helps.